Welcome to the talk Reproducible Experiment Workflows, the Post-Testbed Framework. This presentation was originally held at the Slices Summer School in Finland 2023. I'm Sebastian Gallmüller, and POS was joint work between me and my colleagues Dominik Scholz, Henning Stubbe, Erik Hauser and Georg Karle. Let me quickly go over our motivation. So the motivation to actually create POS was the goal to create reproducible experiments, because researchers typically agree that everyone should strive for reproducibility in experimental research. Our community also has come up with awards to reward this kind of behavior. The rewards look like these. These are artifact evaluation badges that can be awarded to papers that go the extra mile and document their research in a way for others to easily recreate the original results. If we have a look at the history of reproducibility in our community, we can see that there were 2 dedicated workshops on that topic, one in 2003 and one in 2017. And if we have a short look at the problems or at the programs of these 2 workshops, we can see that the problems remained the same over a time span of 14 years. So these artifact evaluation badges are still the best solution we currently have. However, even these badges come with their issues, because to award these badges we need additional manpower for the conferences. We need people that actually try out the experiments and then award these badges. These are typically called artifact evaluation committees, and the problem with this is that not every conference has the manpower to actually staff these kinds of committees and then actually go through the process of awarding these badges. So it comes with a high effort for the researchers themselves to document their research, but also for the conferences. And there's an additional problem called the problem of low robustness. This means that for very slight data changes for the input data, if it's not correctly or not sufficiently specified, this may come or may lead to different outcomes for the results. To better understand the problem of reproducibility, let me quickly introduce the actual definition of the term reproducibility. According to the ACM, reproducibility is not a state, but an entire process. The process has 3 stages, and the first stage can be achieved if the same team executes the experiment using the same setup and recreates the original results. The second stage, that is called actually reproducibility, is achieved if a different team executes the experiment using the same setup again and recreates the original results. And finally, the third stage, replicability, is achieved if a different team executes the experiment using their own setup and recreates the original results. Because in our approach we mainly target the test beds, we also mainly target the first 2 stages, because we target mainly the experimental setup in our test beds. However, if we achieve repeatability and reproducibility, this means typically that we document our own research in a proper way, meaning that it will also become more easily replicable for others to create their own setup. So, how do we achieve that? First of all, we need to clarify how can we limit the effort spent on reproducibility, because this is one of the major blockers that actually hinders some researchers to actually make their research reproducibility, because they see the high amount of effort they need to put into the work to actually prepare it for something like an artifact evaluation. And on the same time, for the artifact evaluators, it can also be quite a high effort. So we want to reduce the workload on both parties. And this we try to achieve by actually making reproducibility part of the experiment design. Meaning that if we design our experiments in a specific way, and if we adhere to this design pattern, we can basically automate the entire setup. Meaning that we go from the setup phase to the execution phase and the evaluation phase of our experiment. We automate this in a specific way, and then we don't need to put additional effort into our experiment, because it was already included in the original experiment design. And on the other side, we also want to solve our second problem, the low robustness problem. This we try to tackle by documenting all relevant parameters for an experiment, and we document the experiment that way. Meaning that if we have all parameters specified in a well-structured experiment workflow, this can also act as the documentation for this kind of experiment. Let me introduce our own solution to the problems. It's called the Plain Orchestrating Service, or short POS, and it's actually a combination of two things. First of all, it's a testbed management system, and second, it's a well-defined experiment workflow. It works like this. On the right, you see a minimalistic setup of our POS controller, meaning that we have a management host or a controller on top of the experiment that basically orchestrates all the other participating nodes in the experiment. And then we have our two nodes that span a minimal network, meaning that we have a load generator on the left and a device under test on the right, and these can basically exchange data during the experiment, and then after the experiment has ended, the controller basically collects the data and performs the evaluation. So first of all, we need to achieve the stage of repeatability, and this we tackle by basically requiring the experimenter to automate the entire experiment workflow, from setup to the actual measurements to the evaluation of the experiment. And at the same time, we only provide live images for our researchers, meaning that the researchers upfront know that they need to automate their configuration, because after a restart, the entire configuration of the machines is gone. This has also the positive effect that there is no residual state in between reboots, meaning that if we have several users working on different experiments, they can just reboot the machines and use them for their own experiments without worrying what the researchers before them did and how to undo their configuration changes. And by adhering to these two facts, the automation and the live images, we basically create a state where our experiments always are repeatable. The next stage, reproducibility, can be achieved if we provide access to this experiment infrastructure also for others, because then researchers can simply log in into our controller, execute the main script of our experiment, and because everything is automated, they can basically rerun the original experiment and get the same results. And by this, our experiments not only become repeatable, but also reproducible. This slide gives a little bit more detail on our experiment workflow. On the right, you can see still our minimalistic setup. We have the controller here in the middle, but also the device under test and the load generator to the left and to the right of the controller. You can also see that an experiment is typically divided into three phases. So we have the setup phase on top, then we have the measurement phase, and finally the evaluation phase of our experiment. So for the setup phase, this is typically where we manage, or the controller manages, the entire experiment using the experiment script. So you basically, as a user, just execute the experiment script, and this basically takes care about handling all the upcoming steps. So first of all, it needs to configure the two nodes, the device under test and the load gen, and can do this via their own scripts. So we have setup scripts here and here, what basically defines the configuration of these two nodes. And we also have specific variables to parameterize these two setup scripts. And these can either be global variables that are valid on all the nodes participating in the experiment. These are these global vars here. But we also have node-specific variables or local variables that are only valid for a specific node, meaning that, for instance, these local variables are only valid on the device under test here. Then, after we have basically set up our machines and provided all the configurations that we want, we can go over to the next phase called the measurement phase. And this measurement phase typically consists of a repeated execution of a specific measurement script. Because we don't want to repeat the same measurements over and over, but we want to have only slight variations between our measurements, we introduced the loop variables. Loop variables are basically what the previous variables were to the setup files, meaning that the loop variables are parameterizing the task description here. So these are the variables that basically define what the task description actually measures. For a network experiment, this could be, for instance, different kinds of packet rates that we want to investigate. And for each run of this measurement script, we can then basically pick another packet rate, and we can also, by associating the loop variables with the results that we create during this measurement phase, we can also create a bundle between the loop variables on the one side and the results that we got on the other. And finally, then, if we have executed our measurement several times, we go over to the evaluation phase, meaning that we basically have all the results collected on the controller, push them into a evaluation script, and this evaluation script can then perform, for instance, create a plot out of all the measurements that we just created. And we also have the possibility to create a publication file, meaning that if we adhere to the specific structure that you see over on the right, then we can also predict where all the files are located, how these files are named, and then we can basically create an automated bundle of all these different files, bundle them together and release them aside a publication. In the next few slides, I will go over the details of our experiment workflow, and we first start with the experiment script on the controller. Here you can see an example of an experiment script on the right, and a short description what actually is going on the right, on the left. So first of all, you need to know the tool that we are using here is also called POS. And the high-level workflow of the script is typically that you want to, for an experiment, first allocate the nodes that you want to have for the experiment. Then you want to load all the variables, then push the config, reboot the nodes, then push the setup script to the nodes that are freshly rebooted, execute the experiment, and then you basically want to deallocate all the resources for others to use them again. Okay, so let me quickly go over the commands on the right. So let's first start with the allocation. So this is the command here. Here you can see basically we need to allocate specific resources before we can use them. We need to allocate them for a certain amount of time. For this experiment, we want to have a duration of 10 minutes. Therefore, we specify the duration 10. And we want to have two different kinds of nodes. In this case, we want to have a device under test and a load gen. These are both mentioned here, meaning that we basically want to allocate two nodes for a duration of 10 minutes. Okay, so nothing fancy here. So let's go over to the next step, the loading of the variables. Here you can see our three different kinds of variables that we want to load. First of all, we have our global variables defined in a YAML file here. And we want to load them as global, so we need to specify them as a global variable. Then we have our two node-specific types of variables. Here we can see that we also need to again specify the specific host. As you can see, for the global variables, we only need one of the hosts participating in a specific allocation. However, the variables will be available on all the different hosts. And it's basically working the same also for the local variables. We have our two YAML files that are specified and loaded into our environment. And then we finally also have the loop variables. These are defined here. Then we need to configure our two machines. So first of all, we need to decide which kind of image that we want to load. Here we want to do experiment with a Debian or Linux Debian bullseye. So we specify it using the command pos nodes image. And then we can basically press the reset button on all of these machines, of course in an automated way. And this is done here, where we just specify the nodes reset command and also specify again our two nodes, the device under test and the load generator. Then we can also wait for our machines using blocking commands. However, we want to have a more smooth way, or if you want to have a more smooth way, you can also execute all the commands in a non-blocking way. And this is what we do here. So we here prefer a non-blocking way. So we specify the non-block or non-blocking flag here. Then we can, after we have basically reset our nodes, also continue to the setup script. This again works using a specific command. In this case, the command's launch operator. And here you can specify an input file. This is the setup script file that I just defined in the slides before. And then we can also use the queued mode, meaning that we basically want to queue all the scripts that should be executed on a specific node. This can also be done with the measurement nodes or measurement scripts after that. Here you can see again that we have two setup files in this case. We have a setup file here and a setup file here for the device under test and the load generator. And then we can basically, after we have done our setup script, we can go over to the measurement phase. This can also be done using the post commands launch command. Here we want to load a measurement script, and we want to use the queued command again for the device under test, but we use the blocking command for the load generator. We use the blocking command here because then basically our entire experiment blocks until all of the measurements and the setup, of course, has been done, and then only the hardware is released. If we would not use the blocking command here, we would basically free our resources before the commands were actually executed, which would be not a very good way to design an experiment. Okay, so this was it for the experiment script. This is basically the only script that is executed on the experiment node or on the management node during the experiment. In the next step of our experiment workflow, we have the setup files. This is an example for such a setup file. As you can see, the setup file typically begins with a get variable command. So these commands are typically here to actually get the information of the variables that we defined in the steps before. Then we use these variables to install the dependencies that we actually want to have for our experiment and run the configuration of our system for the experiment. Then let me quickly go through the script on the right. So in the beginning you have the post get variable command. This is this command, and it actually needs a flag to read the global variables. This is specified, for instance, here. And then we need to basically define our variables that we want to read. Here we want to read the URL of MoonGen that is in the repo MoonGen location. So this is specified here. And then we also want to have our commit ID that we just defined. This is written down here. And this is basically what we want to have to continue our operation. And then we basically need to clone the Git repository here. And then we need to perform specific steps to install our package generator. So we need to change into the directory, check out the specific commit ID here, and then run the build and setup scripts of MoonGen. So these two commands are just defined in the README of MoonGen if you're interested. Okay, so this was an example for a shell script that performs the setup. There's also a different kind of possibility to configure our machines. So for complex setup, we typically recommend to use a system like Ansible. This is a very convenient and also a very typical way, I would say, to configure Linux machines. So you can also use this in our workflow. And there's actually a high degree of freedom for the experimenters. So if you create an image, the Linux image, and this is able to read a specific file or execute a specific script, then you can also use this kind of scripting language to actually perform the setup that you want to do here. After we have specified all our setup files, we can then go over to the measurement phase. And to start with the measurement phase, let me quickly introduce the loop variables. On the right, you can see an example for such a loop variable file. So typically these loop variables are defined as lists. So here we have two different lists, the packet sizes defined up here and the rates defined down here. So first of all, we want to investigate for different packet sizes. In this case, we explicitly specify which kind of packet sizes that we want to investigate. So we want to investigate, for instance, 64 byte, 128, and so on, up to a value of 1518 bytes. For the rates, we have defined it in a slightly different way. So here you can see the abbreviation of a list, and it's a very regular list in this case. So it starts with defining 2 gigabits or gigabit rates that we want to investigate. So here we want to start with 1 gigabit and then go over to 2 gigabit up to a value of 10 gigabit. And we basically want to continue this kind of step width also for the parameters in between, meaning that we want to have, for instance, 3 gigabits, 4 gigabits, 5 gigabits, and so on. For the entire experiment, we want to have the cross product of these two lists to be the goal of our investigation. Meaning that, for instance, for a packet size of 64, we want to investigate all 10 rates that we specified down here. And our framework takes care about this by creating the cross product for us and deploying the right kind of parameters for each specific loop call in this experiment. For the variable format, you again have the choice between YAML and JSON. Here I specified the YAML format. Then, after we have clarified the loop variable file, we can go over to the task description, meaning that this contains the actual measurement file or the script that should be executed for each measurement. The experiment file can be seen here. So here you can see again the high-level overview, just like the high-level overview we had before for the setup script. So we typically start with the variables, or getting the variables that we need for our experiment. Then we have a specific step only for the measurement phase. This involves typically a sync call. The sync call is basically a barrier for the entire experiment, meaning that if we call pos sync on the load generator in this case, it means it will block until the device under test also calls the pos sync command. And this is basically here to define a starting point for the experiment where both nodes are ready to perform the upcoming steps. Then we perform the actual measurement that we want to perform, and then in the end we basically want to upload all the results that were generated on this node to the experiment node, or to the control node in this case. So let me quickly go through the task or the actual script. On the right, here you can see again the pos get variable command, for instance here. And we want to have this for two different kinds of variables. Here the local variable, but also for the loop variable down here. Then we have, as just explained, the pos sync command that blocks until all participating nodes have called this command. And then we can basically start our experiment. As we are on the load generator, we can just switch to our moongen directory. So this is our packet generator, and then execute the pos run command on the packet generator. The nice thing about this convenient script here is that it collects the standard out and standard R of all the executed commands behind it. So this means that we basically run the moongen packet generator, and we can then, or the testbed automatically takes care about saving all the standard output to the experiment controller. We also need to specify the loop flag to actually sign that this should be called as a loop command, where we just use the loop variables that we specified here. And then we basically perform our experiment for 120 seconds. So we generate the rate on the load generator, and then we again kill the load generator using the pos kill command, and we specify which kind of script we want to kill using the name loadgen. So we defined it here initially. The moongen script will be labeled with loadgen, and we kill it down here. And then we basically perform the upload command. This is also a POS tool called POS upload. This also gets the loop argument to just define that this should be annotated with the specific loop variables, and then we specify which kind of file should be uploaded. In this case, the rates.csv file. Again, you can see the example is a simple shell script. This can also be an Ansible script if you have more complex configurations, but in theory you can use any script you like, as long as the image you provide to the experiment nodes will be able to execute the script. Here you can see the workflow for the device under test. On a high level, it works pretty similar. Here you can see the POS_get variable call. Then we synchronize between our two nodes. So we basically block until both nodes have reached the POS sync command. Then we go again into our packet generator. This time we don't want to use the packet generation process, but we want to use the forwarding function of our packet generator. This can again be used using the POS run command. We want to do everything in the loop mode, this is specified here. Then we need to choose a name to actually specify which kind of POS run command we have. In this case, we choose FWD for forwarder, and then we basically create our Mungan call, which is done here, but this time we use the forward function of our Mungan, and then we specify again our two interfaces. Then we sleep for 120 seconds, and then we basically end our forwarding process. Okay, this was it for the actual measurement. And then let's quickly have a look at the result files. Here again, you can see on the right an example of such a result file. We used this time a comma-separated value file, a CSV file, and here you can see a timestamp, a rx_mpps. This is the command for packet rate received, and then you also have a transmitted packet rate. This is the last column in this file. So you always have a high degree of freedom as a researcher, so we used just CSV here as an example. However, it could also be the case that you want to plot the command line output or record the command line output. This would of course also be possible, but you can also choose something entirely different. For instance, you could use standard files like pcaps or something. This can also be done using our POS testbed. The result files are actually annotated when uploading the files to the experiment controller, and they get the loop parameter set as an annotation. So you basically get an ID for each file, and this ID allows you to actually conclude which kind of loop parameter set was used to create this kind of result file. We now have reached the evaluation phase, therefore we need to first have a look at the evaluation file. This is specified here. So we used for the evaluation also an automated file, because only this way the evaluation will become repeatable and reproducible in the end. To actually have a nice tool, we recommend using Jupyter notebooks, one of these example notebooks you can see on the right. So this is a tool that you can use in the browser, and that does a more or less live preview of what you specified in your file. So up here you can basically specify which kind of plot or data evaluation you want to perform, and down here you can see the resulting plot. This is a quite nice tool for debugging and development, but it's also nice because it can be automated, so you can continue using the same file format for debugging, developing, and finally for evaluation. It's also nice that you can do this in the browser, so it can also be done remotely if connected to the machine. Okay, and after this we then go over to the final phase, the publication script. An example can again be found on this slide. So as you have seen on the previous slide, we have a very well-defined workflow where each file has a specific name and a specific place in the entire experiment workflow. And this very strict format allows us now to basically create a script that bundles everything together and documents the entire workflow in a very detailed way. And by bundling everything together and releasing this bundle as a, for instance, as a GitHub repository, you can then also invite others to have a look at the experiment. What you can also do is, because it has a very well-defined script, you can also perform something you can see on the right. And this is basically a bundle as a website. So we basically can create all the evaluation plots and the scripts that led to the evaluation and put it into a website, and then also automate the entire process of creating this website with only little effort or little additional effort for the researcher. So let me also quickly go over a list of recommended tools that I recommended or that I used in the previous slides. So what we always recommend for Testbed users is to use Git for every script that is part of the experiment design. And this can, of course, be used during development, so you always have a valid copy of your Git with or together with a version number. So the versioning system and actually using Git as a backup for our live machines is a very handy tool that we can only recommend to all of our Testbed users. Then there's also typically in networking a package generator involved at some point in the network experiment. So in theory, any tool can be used in our testbed. However, we have designed MoonGen in a way so we can clearly specify which kind of pattern that we want to have for an experiment. And because of this high precision and accuracy that we implemented into our tool, we highly recommend using MoonGen for actually creating reproducible networked experiment. What I can also recommend for more complex setup is to do Ansible or to use Ansible as a tool for the configuration management. This setup script can, in theory, be done in any kind of language, so I just have shown you on the previous slides that it can be done using any kind of scripting language. So for a very simple setup, this is typically enough. However, if it tends to get more complex and you have a script that exceeds, let's say, a few hundred lines of code, it's usually best if you switch to a different kind of tool, and Ansible would be one tool that we can recommend for this task. And then there's finally the Jupyter notebook that we recommend for doing our evaluation. So the evaluation script again can be done in any language. However, the Jupyter notebooks are heavily used in research, so also other projects use this kind of tool. And it's also used by other testbeds, for instance, Chameleon. However, you can also use alternative tools that may be more prominent in your domain. For instance, the CVL that is sometimes used in the machine learning or AI community. Reproducibility is one important aspect when it comes to the design and execution of experiments. However, there are additional aspects you need to consider. One of these aspects is, for instance, the data management perspective. So experimental artifacts should be designed in a way to adhere to the FAIR data principles. So there are specific talks about this FAIR data principles, so I will only go briefly into the details of it. FAIR stands for findable, accessible, interoperable, and reusable. And your data should be designed in a way to agree to all of these 4 features. For instance, it should be designed in a way that others can easily find them, they can also access them, they can also port them between different applications and reuse them in the end. The Slices POS controller currently offers enough flexibility to employ all of these different features, so it can support the well-known data formats and also metadata formats because it offers enough flexibility to support them. And in the end, it's also possible to automate this data collection. However, this part of POS is still under construction, so we will improve this aspect in the future. Let me quickly summarize the results of my talk. POS is, on the one hand, a testbed orchestration service, on the other hand, an experiment methodology. The power of this methodology makes experiments, first, repeatable, because everything in our experiment workflow works automated. It makes them also reproducible, as others can simply rerun the automated POS experiments. And third, it makes it also easier to replicate the experiments because everything is documented and structured in a specific way. So we achieved the goals that we wanted to achieve. POS reduces the effort to create reproducible experiment, and it also documents all the relevant parameters, so it also creates robust experiments. And finally, POS only complements the ASM awards, so we can still have these awards to additionally incentivize creating reproducible experiments. So thank you for listening, and if I piqued your interest, there's also some additional data available, for instance a repository containing all the experiments I just mentioned, and there's also a website available that describes this experiment.